In this video we continue with the notion of parametrization of curves. We recall the notion of parametrized curve. In the case of plane curves, is a function from an interval to the plane that assigns to every value t of the interval a point of that plane. In the case of space curves, that assignment sends every value t of the interval to a point of the space. And remember, a parametrized curve gives more information than its trace. Actually, there are many parametrized curves defined in the same trace. We now see some of these situations. For example, if one has a parametrized curve alpha and one adds a constant to the parameter t, then one has a new curve beta. This is a translation of the parameter, and the interval of the new curve is different. For example, for k equal to 1, if the first curve is defined in the interval a, b, the second curve will be defined in the interval a minus 1, b minus 1. But both curves define the same trace. Another situation is when one changes the sign of the parameter. This is an inversion of the parameter, and the interval of the new curve is again different. And in this case, the direction or orientation of the trace will be the opposite. For example, if we have a curve defined from a to b, the new curve will be defined from minus b to minus a. And if the new curve is, for example, helix from bottom to top, the new curve will be the same helix from top to bottom. Another situation is when one multiplies the variable t by a factor k. This is a dilation of the parameter, and the interval of the new curve is again different. And now, the speed of the trajectory, or the trace, is also different. For example, for k equal to 3, if one has a curve defined from a to b, the new curve will be defined from a over 3, b over 3. And if the first curve, the trace, goes slowly, the new curve will parametrize the trace faster, 3 times. If the factor is negative, the orientation of the trace will be also the opposite. But why is it so important to work with parametrized curves instead of their traces? The point is that the parametrization is usually a function expressed as a combination of elementary functions. These are polynomials, roots, trigonometric functions, the inverse of trigonometric functions, exponentials, and logarithms. And we know a lot of properties of these elementary functions. Then, as a combination of them, we will be able to get information for the parametrized curve. One can think that this is a limitation, but really? For example, taking this combination of elementary functions gives a very complicated curve. It's not easy to guess the trace of it. Actually, we have used a computer to get that trace. By the way, we recommend the use of interactive geometry software, for example GeoGebra. It's easy to find in the web and it's freeware. But now we do some easier examples. To begin with, we give the parametrization of a line. A plane line will be defined as a point plus parameter and vector. The point is a base point and the vector defines the direction. The same applies to space lines, where one has a point with 3 coordinates plus a parameter and a vector. Another important example is a circle. It is parametrized with a cosinus and sinus. And this is a circle with center at the origin and radius 1. If you want to change the center and the radius, then you have to add this new center and you have to multiply the trigonometric functions by that radius. Another example is a graph of a function. Graph functions can be seen as a trace of a curve. For example, if you have a function f, then the curve alpha equal to t f of t gives as a trace the graph of that function. For example, for the function sinus of x, this new curve alpha gives that trace. We finished this video with the helix, as we did in the previous video. The parametrization of this curve is given by cosinus, sinus, and the parameter t times a constant b. The first two components describe a circle, whereas the third one is the height of the helix. Actually, 2 pi b is the lead or pitch per twist of that helix. Finally, the last equation on the screen gives the helix with the vertical axis translated to an arbitrary point of the plane and with an arbitrary radius.